Well, hello everybody. This is Chris McClure again, and we are going to go through the material in Section R.1. So this is essentially our first lecture, and so we're going to get started with some basic concepts that you probably have learned recently or should have learned. But we're going to hit these real quick. I see that a lot of you have already gotten enrolled in my math lab and have already done the orientation as well as the Section R1 homework. But just so that I could say that we've done this, we're just going to go through this material and you can let me know if you have any questions. Okay? So here we go. Let me go ahead and pull up my pen. I am using a tablet PC, and so I have the ability to make markings on the PowerPoint slides. And as we finish the recorded lecture, not only will I render and post the recorded lecture on Blackboard as well as YouTube, I'll post these slides with the ink annotations on Blackboard as well for you to download. These slides are also available blank through the My Math Lab site. All right, so we're going to talk real quick about sets of numbers. Now, the ideal of a set is probably one of the most important and fundamental basic ideas in mathematics is what is a set, and in particular, a set of numbers. All right, in particular, a set is just a collection of stuff, a collection of numbers, typically. It doesn't have to be numbers as elements. It could be fruit or watches or hats or keys or cars or people or whatever. Now, but for the purpose of this class, so it's usually just going to be numbers. All right. Notice that here we've got the set of numbers here. We have a roster of numbers. This is the roster way or the roster style of defining a set. Notice that each of the numbers is separated by a comma. And by convention, we will normally have the numbers in ascending order. Doesn't have to be that way. But just for stylistic purposes, it looks better this way. And we have an opening curly brace that you see there and a closing curly brace, and the entire set of numbers is within that set of curly braces. By the way, we like to give sets the name usually of a capital letter, like D in this case. There are two things that we need to know about set. What makes a set a set? Number one is that each of these elements is listed only once. And not only that, number two is that we need to be able to determine which elements are in the set and which are not in the set. Well, here with this roster method, you can explicitly see that any integer starting off at 0 all the way through 9 is in the set. Because if it's not explicitly listed in the set here, it's not in the set. Just like in a club, how do you know that you're in a club? Well, you'll have a card, or there will be a list or a roster or something. If you're not on the list, you're not in the club. Well, that goes for a set. Another way of defining a set is by listing some sort of property. Using set builder notation, we still have an opening and closing curly brace, but then we use X, it could be Y or N or some other number of the alphabet. And then we have this little vertical bar here. And then we have the property that the number satisfies. So, for example, this says that x such that x is a digit. Well, all these numbers up here are digits. They're single digit numbers, so they're digits. So x such that x is a digit. So these two sets right here are really the same, just two different ways of defining them. In fact, there are other ways, like for example, number line. You can define a set of numbers on the number line by starting off at 0 and making little tick marks. You probably remember the number line, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then placing a dot at each point, at each integer value on the number line. Then this is yet another way of depicting a set that they don't necessarily mention in the book. All right, so hopefully you remember what a set is from previous method. Oh, let me annotate right here. This second way of defining a set is called set builder style or set builder notation. And sometimes you see a vertical bar there, sometimes you'll see a colon instead. All right, moving along. I don't want to spend too much time. So here's a quick example. Here we have a set E, which is the set of even digits. So using the two different ways of defining the set builder and the roster method. Here we have set O, the set of odd digits. Okay. Now, if we have two sets, we can actually combine them by finding the intersection of the two sets as annotated with this notation there. Notice that we have this upside down U there. That means the intersection of two sets, which basically means the set of elements that are in both set A and set B. And you could also take the union of two sets, A and B, which is denoted by this right here. We have this upward facing U. That's actually easy to remember because that upward cup actually looks just like a capital U for union. And the union of two sets is the set of elements that are either in the one set or the other set or both. Okay? So here's a quick example. And notice that all of these examples and all these definitions and everything straight out of the textbook. So I'm not pulling any surprises on you. All right, here's a quick example. We have set A, set of numbers 1, 3, 5, 8. We have set B, set of numbers 3, 5, 7. And we have a set C, 2, 4, 6, 8. Let's go ahead and find A intersect B, A union B, and B intersect A union C. Now, A intersect B is going to be the set of numbers that are common to both set A and set B. And notice that will be the 3 and the 5, because we have 3 and 5 there for set A, and we have the 3 and the 5 there for set B. But the 1 and the 8 from set A will not be in the intersection because those two numbers, neither one of them are in the second set B. And 7 is also not in the intersection because the 7 is not in the first set. So 3, 5 would be the intersection. The union of A and B will be all the elements that are either in A or B or both. So a common way to do this, to write the union, is to just write all the elements from the larger of the two sets and then fill in the missing numbers from the second set. So we have 1, 3, 5, and 8 already. And then from looking at the second set, we already said the 3 and the 5, but then we can throw in the 7 because it's also in there. So notice that all of these 5 numbers in the union. They're either in the first set or the second set, or both. So here's the union. Now, to tackle the third problem, we need to actually calculate the operation that's indicated within the parentheses first. So we'll do A union C. So here's A union C. And A union C, here's A and here's C. Find the union. And it's this set right here. And then take the intersection with B. And that'll give you 3, 5. Okay? All right, moving along here. We could also take the complement of a set. When we take the complement of a set, it's going to be the elements in the universal set that are not in set A. So let me explain real quick what the universal set is. The universal set will be like a kind of like a background set. So, for example, imagine that you have a deck of cards. So you have 52 cards. And then maybe we have some set of, say, I don't know, the set of spades, for example. Then the complement of the set of spades would be the set of cards that are not spades, for example. Now, in this textbook, we will indicate the complement of set A with this notation, with this little overbar here. But in some books, you might see the complement being indicated with this little tick mark there instead. In fact, some books, they even use a little asterisk instead. Anyway, but in this textbook, we'll use the overbar. All right. I don't know if you could hear it, but they're playing taps. I'm on a military post right now and sitting at Fort Jackson, South Carolina. And at 9 o'clock in the evening, every evening, they play taps. Just to put the training soldier, we have basic trainees and advanced individual training soldiers, and their bedtime is 9 o'clock. So that's the signal that it's bedtime for them. All right, moving on here. So we have a set A, and we're going to take the complement of set A. All right, so for example, imagine that we've got a universal set U, the integers from 1 to 9. And suppose that we have set A, the essentially the odd numbers from set U. Okay. Now suppose that we want to calculate the complement of set A. Well, the complement of set A is going to be the elements of set U that are not in set A. So notice that we have 2, 4, 6, and 8. Those are the elements of set U that are not in set A. So notice that set A together with a complement is equal to the universal set. And also notice that A intersected with A complement is the empty set. The empty set being the set of nothing. All right, so that's those are two important properties of the set with its complement. Okay. Now let's talk real quick about Venn diagrams. Venn diagram is nothing more than just a way of depicting the interaction between a set or sets and the background universal set. So we have this Venn diagram where the universal set is depicted in as the rectangle, right? Everything in the rectangle is the universal set. And then within the universal set, we have maybe some set A, some set B, some set C, and so forth. Maybe the sets intersect each other, and maybe they don't. All right. Here we see a Venn diagram with set A and set B. And this shows here that everything that's in set A is also in set B. And if we have a situation where we have where everything that's in set A is also in set B, but maybe there's some stuff that's in set B that's not in set A. So in other words, B is a larger set than A, where A is nestled within B. Then we said that A is a subset of B. And not only that, A is a proper subset if B actually contains something that A doesn't have. So for example, if B is the set of numbers 1, 2, 3, 4, and we have set A, the 1, 2, 3, then we said that set A is a subset of set B. Not only is a subset, it's a proper subset. Now, if we want to leave open the possibility that A is equal to B, meaning everything in set A is also in set B, and everything that in B could be in set A as well. If you want to leave open the possibility that set A and set B are the same, then you could also throw it a little underbar in there. Okay. All right, moving along, here's another possibility for the relationship between two sets. Within the universal set, we have set A and set B, and maybe they don't have anything in common. Maybe their intersection is the empty set, in which we say that the two sets are disjoint. Okay, moving along, and then maybe the two sets have a non-empty intersection, in which case the intersection is not the empty set. So there's the intersection. Everything that's here in the middle, where the two sets overlap, is the intersection. Okay. All right. Here we're showing the union of two sets, A and B, and it's going to be the set of elements that are either in set A or set B, or possibly both. Okay. Here we've got set A, and we have the A complement, which is everything outside of set A. All right, so moving along here, let's talk real quick about the different numbers in our number system that we're going to be using. Now, starting off with the integers. The integers are actually the set of counting numbers which start off at 1, 1, 2, 3, 4, 5, 6, or otherwise known as the natural numbers. And then you bring in 0, you get the whole numbers. And then you bring in the negative counting numbers, and then you'll have the set of integers. So here we have the set of integers. By the way, this is in set roster notation. These numbers these symbols right here, where you have the dot, dot, dot. This symbol is called an ellipsis, which basically, in the context of a set, means to observe the pattern, and then it goes on forever. In this case, if we were to have a set that we could write like this, and if I don't want to write all the intermediate numbers, I could just use the ellipsis and write the last of the series like that, for example. So in this case, the set doesn't go on forever, but you can observe the pattern. Or you can have a different sort of pattern like this. So there's a set of numbers. So is 1/16th in the set? The answer is yes. Is 1/32nd in the set? The answer is yes. But is 1/9th in the set? No. Is 1/20th in the set? The answer is no. All right, so you can kind of see the established pattern there. All right, moving along. So I'm going to erase this stuff here, though. Oops. Let me erase all the ink on the slide here. Now, so we have the set of integers. We also have the set of rational numbers, which include all of the integers as well as any other number that you could write basically as a fraction, as a reduced fraction, where you have the ratio of two integers. All right, as long as you're not dividing by 0, then we're good. Okay. And then we have the set of numbers that cannot be written as the ratio of two integers. Like, for example, if you have a right triangle, maybe each of the two legs is 1 or 2 or some other integer. Well, in this case, we have 1 and 1. And then the hypotenuse, according to the Pythagorean theorem, would be the square root of 2. Square root of 2, it could easily be shown, is not a rational number. You take any circle, like this one right here, and you take the circumference divided by the diameter, and you're always going to get the number pi. It doesn't matter how large or how small the circle is, you're always going to get pi, which is some irrational number, which is approximately 3.14159 ... And it could be shown that pi is irrational. So we have rational and irrational numbers to make up the set of real numbers. So here's another way of depicting the real numbers. Over here on the left, we've got the irrational numbers, and then over here on the right, we have the rational numbers. Within the set of rational numbers, we've got the integers, the whole numbers, the natural or the counting numbers, right here in the middle. Now, interestingly enough, and I'm just kind of say this as an aside, is that in reality, there turns out to be many, many more irrational numbers than rational numbers. But that's okay. But you put the rational and irrational numbers together and you get the real numbers. Beyond the real numbers, we have complex numbers. And we are going to discuss complex numbers a little bit in this class. And then if you go on to take trigonometry, you'll have a lot more discussion of complex numbers in that class as well. But we don't do a whole lot with complex numbers in this class, just a little bit. All right. So here's a quick example. You've got the set of numbers. Which ones are the natural numbers? All right. Well, those are numbers that you can count with. All right. For example, 10. That would be a natural number. Okay. What are the integers here? Well, we've got a -3. That's an integer. And 10 is also an integer. How about the rational numbers? Well, all of the integers are going to be irrational numbers. So the -3 and the 10. But what about numbers that have repeating decimals? Those are also rational numbers. When you have decimals that have repeating numbers or repeating sets of digits, those are rational numbers. Also, if you have a decimal that terminates, like the 0.12, that's also a rational number. So we have the -3, we have the 4/3, the 0.12, the 2.15 repeating, and the 10. Those are going to be your rational numbers. Okay? And then we have the square root of 2 and pi as your irrational numbers. And then all of these numbers are real numbers. Okay? Moving along here. Now, it's not practical to take especially your irrational numbers with all their, non-repeating, non-terminating decimal places and write, because you'll go on forever to go on and write all of them. So you're going to have to cut it off somewhere. Cut it off after 2 or 3 or 4 or whatever decimal places. So how do you do it? Well, you can either truncate or you can round. And sometimes truncating and rounding result in the same approximation. It's really determined what's to the right of the last digit that you want to truncate to. All right, but basically what truncating means is to drop all the digits that follows that specified final digit. So if you want to truncate after the second decimal place, then everything after the second decimal place you'll just drop, regardless of what's to the right. But rounding, you have to use the rounding rule that basically says that you look at the digits to the right of the last digit that you want to round to, and if it's 5 or more, then you'll round up. If it's 4 or less, then you'll keep the digit as the same. So here's a quick example here. Suppose that we've got this decimal number and we want to approximate to 2 decimal places. Well, if we're going to truncate, then we're just going to lop off the 752 and just keep it at the 20.98, regardless of what's to the right of the 8. But by rounding, we notice that the number to the left, the digit to the left of the 8, is 7. So according to our rounding rules, the 8 in the second decimal place will go up to 9. Okay? So the rounded to 2 decimal places number will be the 20.99 compared to the truncated number of 20.98. Just 2 different ways of approximating. Understand the difference, all right? So a little bit more of an example here. We've got these numbers here. Here we've got, the pi out to 5 decimal places. If we wanted to round it to 2 decimal places, then that would just be the 3.14, because the third digit is just 1. It's less than 5. Want to round it to 4 decimal places? Well, here's the 5. Look to the right, that's 9, so the 5 goes up to 6. Truncated to 2 decimal places, we just lop off the 159. Truncated to 4 decimal places, you just remove the 9. Right, so you get the 3.1415. So notice that these 2 numbers are just a little bit different, with that last digit being influenced for the rounding by this 9 right here, where the truncated approximation, that last digit is not influenced by what's to the right. All right, so then we have this number here, the 0.056128. We can round that to 0.06 because of the fact that this digit to the right of the second decimal place of this 5 right here, this number right here is 5 or greater. So that's why we round up to 0.06. Going to round it to 4 decimal places. Well, here's the 4th decimal place. Look to the right. This digit right here is less than 5. So we'll keep this 1 as it is. So here's the number rounded to 4 decimal places. And again, truncating, you just lop everything off to the right of your last digit. So you can see that the truncated number and the rounded number are different sometimes, depending on the number to the right, the digit to the right. Here we've got this number right here, 893.46125. Round it to 2 decimal places. Well, there's your 2 decimal place, or that space between the second and third. So you look to the right, there's a 1, so you don't round up, you just keep it as it is. Round it to 4 decimal places. So according to our rounding rules, see, because this right here is a 5, this 2 will go up to a 3. But the truncation is going to be the same for the 2 decimal places, but that 2 doesn't change for the 4th decimal place for the truncation. All right, so that should be a good example, or 3 examples in this case, to illustrate the difference between truncation and rounding. All right, just as a quick reminder of the various operations that we do with numbers, we can add, we could subtract, we could multiply, and multiply in 2 numbers are indicated by all these different ways. You could also have the little cross that you remember back from grade school. Division can be indicated by those or using, that sort of thing as well. Remember, when you add two numbers, you're finding the sum of two numbers. When you subtract one number minus another number, you're finding the difference between those two numbers. When you're multiplying two numbers together, you're finding the product. When you do the division, you're finding the quotient between the two numbers. All right, so remember your vocabulary. If you want to take the sum of 2 plus 7, which equals 9, you can write it like that. You want to take the product of 3 and 5, which is 15, you can write it like that. The word is can be replaced by the equal sign. All right, moving along here, we're going to evaluate. Folks, we evaluate expressions. All right, be careful about how you communicate what it is that you intend to do. You evaluate expression, which basically means you find the value of. That's what evaluate means. Find the value of an expression. An expression is just some combinations of numbers using the various operations of addition, subtraction, multiplication, division. All right, so we have to make sure that we all agree exactly how we're going to do it and in what order we do the multiplication, the division, the subtraction, and division, and so forth. And oh, by the way, what if there are grouping symbols? So let's agree, let's go ahead and read this together. We agree that whenever the two operations of addition and multiplication separated by separate three numbers, the multiplication always will be performed first, followed by addition. So that probably squares with order of operations that you've learned from a previous class, that multiplication comes before addition. So if you see 3 plus 4 times 5, well, you're going to take 4 times 5 first to make 20, and then plus 3. All right, so you have 3 plus 20 is equal to 23. It would be wrong for you to do 3 plus 4 first and then multiply by 5. No, you just do the multiplication first and then add 3. Or if you have 8 times 2 plus 1, well, you'll do the 8 times 2 first, which is 16, and then add 1 to make 17. If you have 2 plus 2 times 2, well, you do the 2 times 2 first to make 4, and then 2 plus 4 is 6. Okay, moving along here. Now, if you have grouping symbols like parentheses, then you will find the value of the expression within the parentheses first, and then carry out what's outside the parentheses. So here, for this first example, you'll do 5 plus 3 is 8, and then 8 times 4 is 32. The second example here, we have 4 plus 5 is 9, 8 minus 2 is 6, then we have 9 times 6 is 54. All right, here are the rules for the order of operations. Basically says is that you take care of your expressions within the grouping symbols. Now, if you have a couple different levels of grouping symbols, then you work from the innermost set of grouping symbols outward. And then if you have to choose between the multiplication or division and subtraction and addition, well, you'll do the multiplications and divisions first, moving from left to right, and then you do your additions and subtractions. All right, so here we've got some more examples here. 8 times 2 plus 3. Well, you do your 8 times 2 first to get 16, plus 3 is 19. Here we've got 5 times 3 plus 4 plus 2. Well, you'll do the 3 plus 4 first within the parentheses. 3 plus 4 is 7. Then we'll do the 5 times the 7 plus 2. Well, you'll do the multiplication first. If you have to choose between the multiplication and the addition, do the multiplication first. 5 times 7 is 35. And then add the 2 to get 37. All right, so make sure that you observe the proper order of operations. Now, when you have a fraction like you see here for part C, well, think about the fraction bar as a big old grouping symbol, right? You'll take care of what's in the numerator first, as in 2 plus 5. You could write that as 7. All right. Now, in the denominator, you have 2 plus 4 times 7. Well, 4 times 7 is 28, and then 28 plus 2 is 30. And then you have 7 over 30. Okay? For part D here, for this example, you see that you have 2 levels of parentheses or grouping symbols. Well, do the innermost one first. You'll do 10 plus 6 is 16, and then multiply by 2 to get 32, add the 4 to get 36, and then add the 2 to get 38. Right? Observing the proper order of operations. All right. Now, folks, hopefully you've got your graphing calculator here. Make sure that you appropriately use your grouping symbols, primarily your parentheses, carefully and prudently within your graphing calculator. They're there for a reason, folks. If you did not use your parentheses appropriately to carry out this operation, then you would not get the right answer. So here's kind of a screenshot of how you would do that operation on your graphing calculator. All right. All right. So let me also show you something real quick as well. I actually have a graphing calculator with me, and I will show you how this looks like on a graphing calculator. So here's my TI-84 Plus emulator that I've got. I'm going to do an opening parentheses, and then I'm going to do a 2 plus 5 closing parentheses, then divide by open parentheses 2 plus 4 times 7 close parentheses, and then I could go ahead and hit enter. It'll give the 0.2333 and so forth, repeating, or I can go ahead and convert the answer straight to a fraction by going into the math menu, and then under the math submenu, select the first option where you see this arrow fraction. That basically means is convert whatever you have into a fraction. And then hit enter, and voila, you've got your 7/30ths. All right? All right, moving along here, working with properties of real numbers, all right? Again, I'm assuming that you've seen all this stuff, that none of this is brand new. So we'll just kind of quickly go through this. We have the various properties of real numbers. We have the reflexive property that basically says is that a number is always equal to itself. We have the symmetric property that says that if you have one number equals another number, as in A equals B, then that means that B equals A. Transitive property that says that A is equal to B, B is equal to C, that means A is equal to C. The principle of substitution basically says is that if A is equal to B, then wherever you see A in some other expression, you could also plug in B instead. So you might remember the principle of substitution from some other algebra class by taking a system of two equations and taking one equation, solving for one variable, and then plugging that expression for that one variable into the other equation so that you then have one equation with one variable. and then solving for the one variable, and then substituting into the first equation to solve for the first variable. And we're using the principle of substitution in that method for solving a system of two equations with two variables. All right, so here's some examples for illustrating the various properties. For the commutative properties, all right, we have 3 plus 5. That's the same thing as 5 plus 3, because they're both equal to 8, for example. Or you have 2 times 3. That's the same thing as 3 times 2. They're both equal to 6. So those two are equal. So that's the commutative property that says is that if you are going to add any two numbers, you can add those two numbers in any order that you want. And same thing for multiplication. It doesn't matter what order that you add them. That's the commutative property. Commutative, basically, when you think about commutative, think about, going back and forth between your home and work. You're commuting, right? You're going back and forth. So that way you can kind of make a mental connection with the word commutative for this property of addition and multiplication. But not all operations are commutative. So, for example, subtraction is not commutative because of the fact that a minus b is not going to be equal to b minus a for most numbers a and b. In some instances, they might be the same. For example, if a and b are both 0, then this equation would be true. But for most any other numbers a and b, this subtraction is not commutative. All right, moving along here. Now we have the associative property that basically says is that if you are going to add three numbers together, you can do it in any order that you want. If you've got 2 plus 3 plus 4, you can add the 3 plus 4 first to make 7, and then 2 plus 7 is 9. Or you could do add the first two numbers together, 2 plus 3, which is 5, and then 5 plus 4 is 9. They're both the same. Now, associative doesn't mean that you can actually swap the order of the two numbers. This still preserves the order of the numbers. It just means that you can add any two of the three numbers first and then add the other number, and you'll get the same result. Same thing with multiplication. You're going to take 2 times 3 times 4. Well, you can multiply the second two numbers first and multiply the first, right? 3 times 4 is 12. 2 times 12 is 24. Or you can multiply the first two numbers together. 2 times 3 is 6. 6 times 4 is 24. You get the same thing. Associative property holds for multiplication and addition. All right? There's your associative property. Moving along here. Now, here is a very important property, and we're going to use it a lot in this class, that basically says is if you are going to add two numbers together, like b and c here, for this top example, and multiply by the number a, well, you can do the addition of b plus c first and then multiply by a, or you could take a times each of the two numbers b and c, so a times b plus a times c, and then add. Basically says you can add first and then multiply, or you can multiply first and then add. In other words, you would be distributing this multiplier a across the two numbers in the sum. You could also have the distributive property where your multiplier is in the right, outside of the parentheses. And so, in other words, you would be distributing the c to the b and to the a. So here are some examples, right? You have 2 times x plus 3. So that would be the same as 2 times x plus 2 times 3, which is the same as 2x plus 6. Or if you have 3x plus 5x, you could actually factor out the x, like you see here, so you can kind of go in the opposite direction for the distributive property. 3 plus 5 is 8. So this shows you how to collect like terms in an algebraic expression. Or if you want to multiply two binomials together, you can use two iterations of the distributive property. You can take the x plus 3 times x plus x plus 3 times 2 that you see right here as your first distribution, and then your second distribution you're multiplying the x times the x and the 3 and the 2 times the x and the 2 times the 3, and then you collect like terms, and then you have your x squared plus 5x plus 6. All right, moving along here. All right, for our real number system, we have two identities. We have the additive identity of 0, which basically says that 0 is that one number in our real number system that you could add to any other number, and that second number is unchanged. So if you have 4 plus 0, for example, it's 4. 0 plus 4 is 4. 0 plus any number is that number. Likewise, 1 is our multiplicative identity. You can take 1 times any other number, and that number is unchanged. Any number times 1 is that number. 3 times 1 is 3. 1 times 3 is 3. Except, well, even with 0, if you take 1 times 0, you get 0. So that even works there. All right, moving along here. There's your identity properties. Remember, 0 is your additive identity. 1 is your multiplicative identity. When you take the additive inverse of a number, you're taking the negative of it. Now, when we say the negative, that just means that it's just you're applying a negative in front of the number. It's like reversing direction on the number line. So if you take the negative of 6, that means negative 6. But if you take the negative of negative 6, that's going to give you positive 6. All right, the additive inverse of 6 is negative 6. How do you know that you've got the additive inverse of a number? Well, when you multiply the number plus its additive inverse, you get 0, which is the additive identity. The additive inverse of negative 8 is positive 8. Here's what it looks like to take the additive inverse of a number. You have the negative of a negative number, so you surround that first number with parentheses. Otherwise, it looks a little bit strange to have the negative of negative 8. So that's why we have parentheses around the negative 8. Okay? Now, why do we know that 8 is the additive identity, or sorry, the additive inverse of negative 8? Well, because you take negative 8 plus 8 to get 0, or additive identity. So, what is the additive inverse of a number? It's that other real number such that that second number plus the first number is equal to 0. Same thing with multiplicative inverse. What you do is you find, when you're going to find the multiplicative inverse of a number, you're going to find some other real number such that the first number times the second number is 1. So the multiplicative inverse, it's the same thing as the reciprocal. 6 and 1/6 are multiplicative inverses of each other. They're reciprocal, same thing. Because 6 times 1/6 is 1. The reciprocal of negative 3 is negative 1/3. The reciprocal of 2/3 is 3/2. All right. When we say the difference between two numbers, A and B, that means A minus B, which you could also think of as A plus negative B. So 3 minus 2 is the same thing as 3 plus, excuse me, negative 2. All right? Also, if you take A divided by B, you can kind of think about that as A times the multiplicative inverse of B. So 3/2 is the same thing as 3 times the multiplicative inverse of 2, which, by the way, you could write the multiplicative inverse or the reciprocal of 2 or any other number with a negative 1 exponent. Moving along here. 8 minus 5 is the same thing as 8 plus negative 5, which is 3. 4 minus 9 is the same thing as 4 plus negative 9, which is negative 5. All right. Remember that you can think about subtraction by thinking about the real number line. Let's just do the 4 minus 9. So suppose that we got 0 there, and that we locate 4 on the real number line. Well, when we add negative 9, that means that we're going to go 9 units to the left here, which will place you over here at negative 5. Okay? Okay. 5 eighths, or 5 divided by 8, is the same thing as 5 times the reciprocal of 8. Or, in other words, 5 times the multiplicative inverse of 8, or the reciprocal. So, same thing. All right, moving along. Multiplication by 0 as always results in 0. Any number times 0 is 0. 0 divided by any number is 0. As long as you're not taking 0 divided by 0, because we don't know what 0 divided by 0 is. So this would be undefined. So, but 0 divided by any non-zero number is always 0. Because of the fact that you can kind of think about 0 divided by a as 0 times a inverse. And a inverse is some real number, which is always equal to 0. Any number divided by itself is 1. All right, no surprise there. All right, quickly go through these. All right, you take a number times the negative of some other number, and then you can pull out that negative sign out in front. So 3 times negative 5 will be the same thing as the negative of 3 times 5, which is negative 15, for example. Same sort of discussion over here. If you take a negative number times the negative number, the two negatives will cancel. Right? The negative of a negative number will give you the original number because the two negatives cancel. If you have a negative in a fraction, well, you can apply that negative to either the denominator, the numerator, or pull it out front. If you have a negative over a negative, the two negatives will cancel. All right? So, as an example, we have 2 times negative 3, which is the negative of 2 times 3 is negative 6. We have negative 3 times negative 5, which is 3 times 5, which is 15, because the two negatives cancel. We have 3 divided by a negative 2, which really works out to be the same as negative 3 halves, which is the, well, negative 3 over 2, I should say, which is the same thing as negative 3 halves. All right, you have negative 4 over negative 9. The two negatives cancel, giving you 4 ninths. You have x over negative 2, which you could write as negative 1/2 times x. You could even write that as negative x times 1/2 as well, which you could write as negative 1/2 times x. Moving along here. All right. The rules for cancellation apply here. So if you have an equation where there's a common multiple on both sides, then you could divide that out. So for example, you have 2x equals 6, and you know that 6 is 2 times 3, then you can, divide out 2 from both sides. If you have a fraction with a common factor in the numerator and denominator, well, then you can cancel out that common factor. In other words, you're reducing your fraction. So if you have 18 12s, for example, 18 12s, well, 18 is 3 times 6, 12 is 2 times 6, then take 6 divided by 6 to give you 3 halves. Okay, moving along here. We have the zero product property that says if you have the product of two numbers equals 0, that means that at least one of those two numbers must be 0, or possibly both. So in fact, we use this property a lot when we solve algebraic equations. You have a product of two things or more than two things equals 0, at least one of those factors has to be 0. So we set both factors equal to 0 and solve the equation. So for example, we have 2x equals 0. That means either 2 is equal to 0 or x is equal to 0. Well, look, we know that 2 is not equal to 0. So that means that x must be equal to 0 in order for this equation to be true. For example, here we're using the zero product property. We will use this many times. All right, we're almost done, folks. This has to do with the combining fractions. Now, remember that in order for you to add or subtract fractions, you need to get a common denominator. So that means you need to find the least common multiple of the two denominators. In other words, find the LCD, the lowest common denominator. Okay, and then once you do that, then you have to change the two fractions so you have to find a common denominator, and then you can add the two numerators. In order for you to multiply two fractions, well, you multiply the numerators together, multiply the denominators together. If you take one fraction, divide it by another fraction, that means that you take the top fraction, multiplied by the reciprocal of the second fraction. All right, so a over b divided by c over d is the same thing as a over b times d over c. So you just invert and multiply. So here's some examples here. Suppose that we've got 2/3 plus 5/2. Well, the least common multiple of 3 and 2 is 6. So you take the first fraction, multiply by 2 over 2. Take the second fraction and multiply by 3 over 3, so that you'll have a common denominator of 6. And then you can just add the two numerators, the 4 plus the 15, to give you 19. So you get 19/6 as the result of the sum of those two fractions there. Or if you're going to take a 3/5 minus 2/3, so again, you need to get a common denominator, which would be 15. So you multiply this first fraction by, 3 over 3. Take the second fraction, multiply by 5 over 5, and then add the numerators. All right, which would give you the result of negative 1/15. All right, if you take 8/3 times 15/4, so you can just go ahead and multiply the numerators together, 8 times 15, multiply the denominators together to give you 3 times 4, and then make sure that you reduce appropriately. For example, you see a 4 in the denominator, there's an 8 in the denominator here, so and 8 is 2 times 4, so you can cancel 4s. Also, the 15 is 3 times 5, so you can cancel 3s. That gives you 2 times 5 over 1, which is just 10. Okay, so suppose that you got 3/5 divided by 7/9, that would be 3/5 times 9/7. Combine numerator, combine denominator, you get 27 over 35. Now, let's just do a quick refresher on how to find the LCM of two numbers. So, as a quick example, we have 15 and 12. What is the least common multiple? Well, one way of finding the LCM is just go through and take the first several multiples of each of the numbers. So we can start off with 15, and 2 times 15 is 30, 3 times 15 is 45, and so forth. So as we go from one number to the next, we're just adding another 15. So you got 45, 60, 75, 90, 105, and so forth. Then we do the same thing with 12. We have 12, 24, 36, 48, 60, and so forth. And then find, the first number that appears in both lists. which in this case is 60. Now, another way of finding the LCM of 12 and 15 is by taking a look at the factorization of each of the numbers. Now, 15 is equal to 3 times 5. 12 is equal to 3 times 4. So the LCM, it has to have a 3, it has to have a 4, and it has to have a 5 in order for it to be a multiple of both 15 and 12. And this gives you 60. Okay? Just a different way that they don't necessarily show you in the textbook. Okay? Moving along here. So, suppose that we needed to add 8/15 to 5/12. Well, we now know that the common denominator would be 60 because that's the LCM of those two denominators. All right, so what do we need to do to get the denominators to be 60? We multiply the numerator and denominator by 4 for the first fraction, multiply the numerator and denominator by 5 for the second fraction. All right, and then we'll have that common denominator of 60. So this first fraction becomes 32/60ths. Second fraction becomes 25/60ths. Now look, 32/60ths is really the same value as 8/15ths. 25/60ths is the same value of 5/12ths. So we're not changing the value of those fractions. We're just rewriting them so that those two fractions have a common denominator. Now you can add those numerators, 32 plus 25, to give 57. So 57/60ths is the sum of these two fractions. All right. Same thing for subtraction. You need to get a common denominator. Okay. By the way, your final answer should be reduced appropriately. 57 and 60 both have a common multiple of 3 that you can cancel. All right, and that's it. Excuse me, for section R1. All right. Now, I've posted homework for you to look at. Some of you have already accomplished it. Good for you. Everybody else needs to get in there, get registered with my math lab, and make sure that you do the orientation homework, and then the section R1. And that should go pretty quickly for you if you understand this material, which, by the way, you really should, because this material was covered in a previous section. But I also realize that a lot of you, it's been a while since you last took algebra, so that's why we're doing this. Not all teachers hit the front matter so much. That's okay. We're going to go through all of chapter R. My next recorded lecture will be section R2. So go ahead and take a look at that before watching the next lecture. Okay? So have a good day, and I'll record another lecture on Thursday, May 23rd. All right? Take care. Good night. Best wishes.